Hey, welcome back AP Calculus students. Today we're looking at 8.5 applications from science and statistics. We're going to be spending 2 days on this. This is part 1. So we're just going to be applying all the things that we've learned from about and from our integration and our antiderivatives and stuff like that. All right, so the first one says find work done by f of x equals cosine pi x along the x-axis from 0 to 1 meters. Okay, so for these ones, it's pretty easy. The force done, the force done by any function, all we have to do is we're going to find the integral of it, and we're going to, yeah, that's pretty much it. We're going to find the integral of it. So we're going to find the integral. The start is at 0. The end is at 1/2. And then our function is cosine pi over x dx. All right, now this one's a little bit tricky because we do have to, we have this inside value, the pi x, which is not going to just derive nicely. So we're going to have to do our u sub here. So we'll say our u is pi x, then our du would be pi dx. Right, so we need to have a pi dx here before we start integrating. Actually, let's do it this way. So remember we said that if we do a u sub, then we can say cosine u. Actually, before we do that, let's do what we were going to do originally. 1/2. All right, so for our the thing that we're integrated, we need a pi in there with our dx. So we're going to do 1 over pi outside. We're going to do pi inside, cosine pi x dx. All right, so now we can do that the trick we have with our u sub. So we can say we have our du and our cosine u. So cosine u du and 1 over pi on the outside. And then we said that we can just do our starting and end points if we plug this into our u, right? So pi times 0 is 0. So the cosine at, sorry. So if we plug this in, then we get 0. And then when we plug in 1/2 into our pi x, we get pi over 2. Okay, so now we do our integral. So the integral of cosine, I always get this mixed up, I believe is sine. Let me just check my sheet to make sure. The integral of cosine is sine, correct. So we're going to do sine u from 0 to pi over 2 times 1 pi, or 1 over pi. All right, so we're going to do 1 over pi. Sine of pi over 2 is 1, minus sine at 0 is 0. So it's going to be 1 minus 0 is 1. This whole thing is 1 over pi. Okay, so again, when we're doing our work, all we do is find the integral of our function and then simplify. Okay, the second one's kind of long, but it's not too bad. It's good that it's long because it breaks it down into separate parts. Otherwise, it might be overwhelming. So it says that a leaky bucket weighs 22 newtons empty. So that's just the weight of the bucket. It's lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 newtons per meter, N over M. The bucket starts with 70 newtons of water, but it leaks at a constant rate and finishes draining as the bucket reaches the top. Find the work done. Okay, so we're going to find this in parts, which helps us to get the whole picture easier. So it says that the bucket weighs 22 newtons. So if we're trying to find how much work is done to lift the bucket, then we're starting at 0, we're lifting it 20 meters, so that's the end, and then we have 22 newtons. I guess we'll say this dx because they're not telling us what our variable is. So when we do our integral of any constant, what's going to happen here is we're going to do 22x is the antiderivative, and we're going from 0 to 20. So this is going to be 22 times 20 is 440. And then if we plug in 0, we get 0. So this is going to be 440. I believe it's in newtons. Yeah. Okay, so 440 is how much work it takes to lift the bucket the 20 meters. Okay, on to part B, lifting the water. So the water is a little bit trickier. So the water is leaking out of this bucket at a constant rate. So here's the bucket of water. On the bottom, it's full of water. That's going to be 70 newtons worth of water, I believe. Yeah. But as we lift it, when we get to the end of the 20 meters, on the very top, it's going to be empty. There's not going to be any water in there. So we have to figure a way to represent that weight of the water as it's leaking out. So we're going to say, okay, 70 is the total. Right, so we're going to say 70 is the total. So at the very beginning, at 0 meters, it's going to be full. Right, so let's make a ratio here out of 20. So think about this part in here. When x is 0, 20 out of 20 is one whole bucket times 70. So that matches, right? So at the bottom, that matches out. Now when it gets to the top, we'll put in a 20 in for our x. 20 minus 20 is 0, over 20 is 0. So that's 0. That's none of the water that's left over. So as it goes up, some of the water is spilling out. This parentheses part gives us the ratio, well actually the fraction, I should say, right? Fraction of water left in the bucket. Now, if it weren't being pulled constantly up by the same amount, or if the water wasn't flowing out at a constant rate, then we'd have big trouble. It'd be like way harder. But because it's being pulled smoothly up to the top, and because the water is draining out at the same rate the whole way, and it empties out at the very top, then this part's a little bit easier. Okay, so let's do our integral here. We can actually simplify this. So if we multiply the 20 out, then we get 70 times 20 is 1400 minus 70. Whoops, minus 70 x over 20, and then we can divide it by 20. So we get 1,400 divided by 20 is 70, minus 70 divided by 20 is 3.5x. And we did that because it's going to make our job a little bit easier when we do our integral, right? So we're doing the integral from 0 to 20 again, right? Because it's being lifted from 0 to 20 meters. Yeah, meters of 70 minus 3.5x. So this is going to be, sorry, I'm running into the next part. This is going to be 70x minus 3.5 divided by 2. What's 3.5 divided by 2? 1.75 x squared from 0 to 20. And then when we do that math, we end up with 70 times 20 minus 1.75 times 20 is 1365. Oh, sorry, it's squared. Sorry, I forgot that. So 1400 minus 1.75 times 20 squared is 700. Okay, so the lifting the water takes 700 newtons to go along with the one that we had earlier, which was 440 newtons. Now let's do the rope. So the tricky part about the rope is, yeah, you're pulling the rope, but as you're pulling the rope from the bottom, you're pulling more rope here. So the weight of the rope is the whole rope, as opposed to when you're nearing the top, you're pulling a shorter section of rope. Right, so even though the rope doesn't weigh much, it does affect the amount of work we're doing on the rope. So we're gonna set up our integral in this way. So whoops, kind of like we did with the bucket, but because it's not leaking out, it's gonna be a little bit simpler. So here's the weight of the rope, and as we're getting to the top, we have less rope. So think about this one. At 0, right, we're lifting the whole weight of the rope. We're lifting the 20 meters worth of rope. When we get to the top, we're lifting 0 rope because 20 minus 20 is 0, and we got no rope left. We don't have to take a ratio of it because we're just talking about the length of the rope. So we're doing this from 0 to 20 as well. We should probably simplify this like we did the other one. So 0.4 times 20 is 5. And then we can do our integral here. So it's going to be 5x minus 0.2x squared from 0 to 20. Okay, and then 20 times 5 is 100 minus 0.2 times 20 squared is 20 joules. Oh, sorry, this should be 8. I miscalculated. 0.4 times 20 is 8. Okay, so let's recalculate that. 20 times 8 is 160 minus 0.2 times 20 squared is 80. There we go. So this is 80 joules. Okay, so we're just adding the 3. So the work done for the bucket is 440. The water was 700. And then the rope was 80. So altogether we end up with 1,220 joules of work. Okay, so we want to spend some time on this. These are the type of problems that you might see on your end of course exam. So we want to practice them, get comfortable with them, and get prepared for our test, which is coming up very soon. Good job.